So you are welcome to this weekend workshop on correlation and linear regression. Let's quickly share the timetable. This is the timetable of what we'll be doing. The 3 days. You see, the first batch last weekend was the first batch, and this is batch B now. Understanding the concept of covariance. So today we'll look at. Today we'll be discussing. I think we'll look at correlation entirely. Then by tomorrow and next tomorrow will be on regression. So under correlation, we'll look at understanding the concept of covariance. Correlation, the standardized covariance, correlation coefficient, Pearson, gamma, Kendall, even some other one like pi-Syria and point pi-Syria. We also look at the type of correlation as per bivariate or zero order, and partial and semi-partial correlation. So we want to, let's quickly, okay, by tomorrow, we look at linear regression, method of least square. Okay. So, okay, thank you. Assessing the goodness of it, coefficient of determination, which is the R square, regression coefficient, creating dummy variables, controlling for confounder using multiple linear regression. So we'll be looking at all this. I wouldn't know if, because some of us, or most of us here, were here last week, and some are new. So I don't know if there are expectations, what we expect to learn, because though I've shared the timetable, but maybe there's some expectation what we expect to learn that are not captured in the timetable. I just want to give us 1 minute or two. If anybody has such, what you expect, what are your expectations in these 3 days? No, don't mind, it's a workshop, even though it's virtual. You can be sure that it can be even more practical than physical workshop. That is what I've discovered. Because statistics is a formal science, so the practicality of it is not in laboratory. It's a branch of mathematics. And now that the technology has given us leverage on solving statistics, and computer and internet is you know what I mean by that. So when the first time when I wanted to start the workshop on SPSS, somebody, I think the comment was from Makurdi, said, how do you want to use it, demonstrate SPSS on Zoom? I just laughed. And it's practical. I've discovered that it is even easier for me to demonstrate SPSS, to do all this practical on Zoom than physical, because during the physical workshop, if by the time I demonstrate, somebody is only my own computer is projected, so everybody has his own computer, and if anybody has issue, I have to be going one by one, and some of them are having the same issue, and by the time you spend this time here, you go to another place having the same issue. But sometimes when you even waste time, people now say, oh, let's proceed with Zoom. The person that's having issue, share it. You can actually share it, and everybody will see it. So if another person is having the same issue, you don't need to, ask again. Once one person share, you're able to see it, everybody see it. So can you see? So it is easier. To me, I even find it more interesting demonstrating statistics on Zoom than the physical. So I wouldn't know if anybody has expectation. I want to give 1 minute. If you cannot talk, you may shout it. If you don't want to say anything, you can shout it. I will read it out. Nobody? Nobody has expectation? Okay, I think we'll proceed.
Thank you, sir. It's just to strengthen my knowledge of what I already have, just to strengthen the knowledge of it. Thank you, sir.
Okay, that's great. I was calling
I'm
you.
just
It's like you
by the
left
time
the
we
machine. I was calling you before. Like you left the place.
Oh,
Okay, any
sorry,
other one?
sir.
No problem. Any other one?
no, it's just I believe by the time we go through everything on the timetable, that would be good enough for me as a person.
Okay, that's great. Thank you, sir. So any other one? Because sometimes you may be expecting and you feel that it's not on the timetable. That's why I'm saying that. You know what I've displayed on the timetable. Sometimes you may feel okay. I feel this one should be part of regression you want to learn or correlation. Okay, if there's no, let's just start right away. Just a minute. So as I've said before, today we'll start with correlation. So the modality of the workshop is a little bit different from that of the lecture. The lecture, I try to finish the lecture before I entertain question, but the workshop, I just talk a bit, I ask for question. If you have question, don't hesitate to stop me because this is, to me, I consider this one the most serious business than the lecture because the lecture is more like public lecture. Why for somebody to devote time out of busy schedule to attend the workshop and pay for it also, it's not a joke. So you have to make sure that you maximize every opportunity. So in everyday life, to denote correlation in everyday life denotes some form of association. And you can shout your question also along if you know, so that once I see it, I can just pause and address it. So in statistical terms, we use correlation to denote association between two quantitative variables. That word quantitative variable has to be there. Quantitative. So when you are talking of two variables, the two variables must be represented by a number. That's what it means. Although the origin, you're going to see the origin of correlation has to do with continuous variable, but it's being used also to look for association between variables that are not continuous or between continuous and the one that are not continuous. But even variable like ordinal variable that naturally they don't carry number, but they only carry the number that are given as a code, like SK, agree, strongly agree, all those things. They don't have number, they are qualitative. But because the scale of measurement is ordinal, in the sense that we know that strongly agree and neutral, there's a gradient. So in that case, you can use that liberty to appoint number, to put number, and that is the logic behind putting 1, 2, 3, 4, 5, even up to 10. Of course, for anything to be on ordinary variable scale, there must be at least 3 categories. You cannot have 2 categories and talk about ordinal. It has to be at least. I usually start from 1. Sometimes I use 0, 1, 2. But whichever way, there must be more than 2 categories. So even in those situations where you now use ordinal variable, but you have already given number, and that is why correlation has to do with two variables with number, quantitative variable. So that is the difference between the way we conceptualize research in health and other fields. many other fields, maybe maybe in arts or whatever. Sometimes they talk about correlate. They use it like the way you use any English, everyday usage of English. Correlate something that has nothing to even do. They can even know with number, or that has nothing to do with it ordinal, that there's no gradient. Like some people can say ethnicity, they are trying to correlate ethnicity and something. You know, in medical research, it doesn't make sense. It doesn't make meaning, because correlating anything that you cannot, there's no gradient. Ethnicity has no gradient. You know, just like a geopolitical zone now. There's no one that is higher than the other. They're just like sex, male and female. We know that two categories. They look at marital status. No, married, divorced, no, single. Those are different categories. There's no ranking attached to it. They are not like they are not on ordinal scale like socioeconomic status or some rankings on profession like military, like even the health also in medical profession. There's ranking, prof, consultant, senior registrar, medical officer, then student, medical student. Also in most of the health professional, no professional group, you have that like nursing profession. There's ranking for each category, different category. So in that case, you can allot number, but you cannot talk about correlate when something, the variable is nominal. No. But it does happen in other fields. So we assume that the association is linear. That is, linear, the word linear here means that if one variable increases or decreases by a particular amount, the other one decrease or increase by a fixed amount. That is, if age and weight vary, if your weight and height vary together, if weight increase by 5 kg, height increase by maybe 2 centimeters. If the weight still increase further by another 5 kg, the increase in the height will be same 2 centimeters. That is where the linearity is. But of course, there are some things also, after a while, they may be linear to a point. After that, the increment may not be linear. In that case, no more linear. It may begin to even decrease. But when we talk about linear association, when one increases or decreases by a certain amount, the other one reciprocally increases or decreases by a certain amount also. And it's like that. Regression involves estimating the best straight line to summarize association. So here, correlation, we just talk about degree of linear association. But if you want to depict, maybe determine the value of one from the other, is outside the realm of correlation. We are talking of regression. We'll not talk much about regression because by tomorrow we'll be talking extensively about that. But you see that they are related. Even when we talk about regression, you see that correlation has a role to play there. Now let's quickly look at association and relationship. Correlation describes the strength of an association between two variables. So correlation is symmetrical in the sense that if you say correlation between A and B is the same thing correlation between A and B and C. If you even want to plot graph to depict it, anyone can be on the y-axis, vertical or horizontal. That is the concept of correlation. So in correlation, there's nothing like, even though you know that by looking at two variables, one may be the exposure, the other one the outcome. The correlation in correlation, the usage over time, people just, are just silent about that. You don't want to talk about dependent and independent exposure outcome. Just two variables, just a crude way of looking at strength of association between two variables. But when we now talk about dependent, independent, we are now talking of relationship. That is the realm of regression. So in regression now, y is the dependent variable, y X is an independent variable. So the relationship you describe as the regression of Y on X. I think we'll talk about that tomorrow when we talk about regression, origin of regression. So you always see that you are regressing the outcome on the exposure. It's very funny. But that is just the logic. We'll discuss that tomorrow. Now, let's come back to the correlation we are discussing. And for us to be able to understand very well correlation, we must understand the concept of covariance, because those that first describe it, they actually describe it from that covariance. It was Gartin that first of all talked about, coined the word correlation. And his student, Carl Pearson, took the work further and brought out the understanding of correlation from covariance. Covariance is a measure of how much two variables vary together. So if you remember variance just means how a particular variable vary in value among subjects in the population. That is variance. How spread are the value around the center. The variability, how spread, how different are the value in the population. That's what variance look at. And when we talk about variance, standard deviation variance, they actually mean the same thing somehow, because just like standard deviation and variance is like water and ice block. If you need water, someone give you ice block, allow you to mix, you get the water. Or if you need ice block and it's water you got, you put it in freezer to freeze it. So just like standard deviation is square root of variance, variance is square of standard deviation. Both of them are measure of variability. But when we talk about variance, okay, let's just call it variance. How the value of a particular variable vary among subjects. While covariance, so when you have two different variables or many variables that vary on their own, like x, y, using x, y is just for convenience. If you call this one x, the other one is y. So we have two variables. One is denoted as x, one is denoted as y. Both of them have their variance. But if peradventure, as one vary, it affects the other, almost they affect themselves, somehow. They tend to vary together. So the degree to which they vary together is the covariance. So covariance is similar to variance, but variance tells us how a single variable varies, while covariance tells us how two variables vary. So like now, if you want to represent a particular variable, you can only do that on a straight line. But when you are having a plane figure, vertical, horizontal like this, you may want to see how two vary. So a line is just for us to know something is increasing. So along the horizontal, let's say one variable is along the horizontal in this graph you are showing, another one is along the vertical. In this first one, as this horizontal is increasing in value, you can see that the vertical is decreasing. Look at the first point here, is at the height of the vertical value at the beginning of the horizontal. So that as this one, the vertical value is decreasing, the horizontal one is increasing. And if you start from here, at the end here, that's the lowest point for the vertical and highest point for the horizontal, the one along the horizontal. So as the horizontal is increasing, the vertical, as the horizontal is decreasing, the vertical is increasing. So in that case, what is just showing us that there's a negative covariance. As one increases, the other one decreases. The opposite is this last one, which both of them, if you look at it now, if you start from 0, from this left corner, which is the origin for both of them, as this one increasing, you can see, because each dot is a combination of where the vertical value and the horizontal value meet. So as the horizontal increases, the vertical increases. So when it slants up from left to right, up, that is positive slope. We are going to see that later. So that shows that both of them increase together. The first one, as one increases, the other one decreases. So this first one, and I said, for the fact that they are on a straight line, that shows that it's more like a perfect large negative covariance. That is, they vary together negative in the sense that as one increases, the other one decreases. While this other one, the third one, is positive as one increase. Both of them increase together. If one decrease, the other one will decrease also. So they move in the same direction. So there is positive covariance there. This middle one, there's no pattern in the sense that you cannot even say there's no covariance. They didn't vary together. You can't say if this one increase, the other one decrease. So they have nothing common as far as change together. Now, let's illustrate variance and covariance so that we have a mental picture. Why I try to do that is that the brain records information in picture. The brain, our brain, do not record information as number as we think on letter. It actually record information better in picture. So when you have a mental picture of something, it makes it better for you to understand. Now I want to quickly illustrate variance and covariance. Now we want to use example of some people watching adverts of a particular product and also buying some packet of the product. So there are 5 people here. Number 1, subject 1 to 5. So these are the number of adverts watched, maybe on the television. The first person watched 5, 4, 4, 6, 8 like that. So the second person 4, 4 like that. So first person watched 5. Then this is the number of packet bought. He bought 8 packets. The second person watched 4, bought 9. Third person watched 4, bought 10. The fourth person watched 6, bought 13. The last person watched 8 and bought 15. This is the mean number of adverts watched. After adding together and divided by 5, this is the mean, this standard deviation. For the number of packet bought, this is the mean 11, this standard deviation. If you have to put it in graph, the blue graph will show the advert watch, the green one, the packet bought. You will see that the horizontal line is the mean for each of them. So you know the mean for advert watch is number of advert watch is 5.4. So that's why you have the line between 4 and 6 here, 5.4. While the mean for the packet bought is 11, which is between 10 and 12 here. Can you see? Now you see each value for the first 3 advert watch and packet bought, the value of each are below the mean. That's why you see. So the difference between their value and the mean is the line joining the mean and the value. Because they are below the mean, so this difference is negative. Because you are removing mean from each value. So when you remove mean from value that are below the mean, the difference will be negative. For the last 2, their means, the values are above the mean. When you remove mean, you see our value, the difference is positive. So from what we can see, the way the picture is, we can actually say both of them vary together, okay, co-vary, in the sense that in the same direction, like a positive covariance line, in the sense that if you look at how do you know? So for the first 3, the advert watch, they were below the mean, and the same thing with packet bought. The first 3 values are below the mean. So the last 2 value advert watch above the mean, for the packet bought also above the mean. If let's say they vary in opposite direction, and what will have happened is that as the first 3 advert watch are below the mean, then the first 3 packet bought will be above the mean. That will be the opposite. And as the last 2, the advert watch is above the mean, the other one will be, the other 2 packet will be below the mean. So they will be in opposite direction. That shows that they co-vary in opposite direction. But if there's no covariance at all, if it don't even vary together at all, there won't be any pattern. What you will see will be just stagger. You won't see any pattern. No, this one can be up, this one down, this one just faster. That shows that there's no covariance. Now, if you are to calculate the covariance here, you know the variance for, you remember the formula for variance for X now. If let's say the advert watch is X and packet bought is Y, now X, you know, X minus S bar over N minus Y. You know, those are the basic things I expect everybody to go watch. Now, here, X minus S bar, that's deviation. Square it, average of it, which is the division by not N, but by degree of freedom. That is the variance. So this is the variance. It can be written this way. You split into two. X minus x bar square. You can write it 2 times. That's what I just did. The same thing with y. This is the variance of y. X minus y, y minus y bar square can be written like this. So their covariance will be just one of them. So this and this. So x minus x bar, y minus y bar. That will be that's the covariance. So if those one are the variance, this is the covariance. And if you, all you need to do, you put x, y, x minus x bar, y minus y bar, multiply the two. If you sum it together, 17. Put 17 over n minus 1, which is 4. Because the total number is 5. So this is covariance. Now, covariance is very funny. You need to imagine, you've not even heard much about it because it's not useful much. The reason is that there is problem interpreting it. What we just got now, if the value of correspondingly maybe the value of packet board, advert watch, and packet board double for each of them. If you double for each of them, the relationship has not changed, but the value of covariance is going to be maybe double, bigger. So that is one. Then if another maybe variable involved have naturally bigger unit of measurement, like discussing kilometer, how many kilometers travel by plane or by car. So we're talking of 1,500 kilometers and over 12 hours. So you will see that the value will be bigger also. No, two things affect it. If the value of those things increases, the value of covariance will increase. If the value of those things increase, the value of covariance. If the unit, the bigger the unit, the bigger the value of covariance is not standardized. So because of that, it's not useful much for comparison. So that was what brought the intelligent people now. What shall we do? That was why they now try to fix the problem of interpreting covariance. I think before we move further, because fixing the problem of interpreting covariance was what brought correlation. So I want to entertain question. I don't know if there's any question before we move further. If there's any question from what we have just discussed. Dr. Additional, we were late. We will be waiting for you. Any question? Dr. Additional, are you there? You have to unmute yourself if you want to talk. You have to unmute yourself.
Okay.
Yes.
Hello, I said I'm fine. I was a little bit late.
I said you came late. We will be waiting for you.
Yes,
okay,
yes, a little bit. No
okay.
question till now.
Okay.
I understand everything we have discussed so far.
Oh, that's great.
Okay.
Any other? Yes,
I was
sir.
trying to just clarify something.
Okay.
Where you were introducing correlation,
okay,
and you made measure of Likert scale, which like a district an ordinal variable, like in ordinal form when you quote questionnaires. Are you saying that correlation can be applied to that kind of data?
That was what I said. Why I said that was that I said that
I was seeing that some people are saying that before you can use that, you require an interval or ratio scale.
that is a type of correlation now. That's why when we talk about different type of correlation coefficient, Pearson correlation coefficient.
Okay.
Those are the ones that you need interval or ratio scale. Yes, I mean, though the origin of correlation started with that Pearson correlation, and most of the advancement in statistics come with continuous variable like that. But of course, we know that we have a lot of variables that don't have the same characteristics as continuous, and we need to solve the problem in life. So intelligent people have a way of adapting those things to suit the categorical. That was how Spearman, Kendall now came in. So all of them are correlation. So the only thing that is common there, I said, is that It has to do with quantitative variable, degree of association between two quantitative variables. So even if that thing was not quantitative originally, in as long that you give number, so like the like say you are talking about now, normally they are no number, but because it's ordinal scale in the sense that you can talk about more than or greater than or less than, but you don't know how much more than. So because of that, people just look for convenience. You just when you list the different categories, you just give arbitrary number 1, 2, 3, 4, 5. But in the real sense, between strongly agree and agree, in real life, when somebody is answering the question, you cannot actually establish that the distance between strongly agree and agree is the same thing between agree and neutral, and the same thing between neutral and disagree, and the same thing between disagree and strongly disagree. Nobody can establish that. But for convenience, we just put 1, 2, 3, 4, 5. Just like when you do your clinical scaling also, when you want to look at the severity of disease, you say moderate, severe, mild, moderate, and severe. Very severe. So between mild and moderate and severe, there's no standardized measure. Because when you are assessing it, what I call severe may be different from what, in fact, some people, what I say is severe. When I assess it, you may say it's moderate. So somehow, it's subjective, but for convenience, you now put 1, 2, 3, 4, 5, give. But in as much that when you are doing the correlation, the number, so the correlation has to do with number. As this one increases, does this one increase by a certain amount? That's it. Have I answered your question?
Okay.
So the type of correlation now matters. Yes. Okay. Should we proceed? Yes. Fixing the problem of interpreting covariance now. The covariance, the problem can be fixed by dividing the covariance by the standard deviation of X and Y to get correlation coefficient. This one is just exactly like what happened when intelligent people like Carpesian and Fisher, when they look at normal distribution, they know that many variables follow normal distribution. Height, weight, many biological variables and social science variables follow normal distribution. Many naturally occurring variables follow normal distribution, in the sense that as the value of that variable increases, the number in the population that have the attribute increases also, until it reaches a certain level where it will increase further, the number begins to decrease. So you are now having some extremely small, some extremely big value. Then the majority we have value that are not extremely small and not extremely big. There are many variables follow that, but if you plot the graph also, you see that you're going to have different scale, because just like what I said, different variables come with naturally different scale. Even though with all this international system of measurement, SI unit, it didn't solve the problem completely, where we have one standard measurement across the globe. It only solves it for that particular variable, but you cannot compare two variables in their distribution, two variables that naturally they have different units. And we are not talking of the same variable that you have different units, like weight, kilogram, gram, all those stuff. But like weight and height, they are different variables. How do you compare them? So intelligent people now say, okay, instead of talking about your weight, now I say you are 90 kg. They now look at, okay, what is the mean weight in the population? The mean weight is 70, and maybe the standard deviation is 10. So they want to know how many standard deviation are you away. If you remove the mean from your 90, 70 from 90, it give you 20. If the standard deviation in the population is 10, divide 20 by 10, it give you 2. That shows that that person that is 90 is 2 standard deviation above the mean. If somebody, another person is 50, is minus 2 standard deviation, that is 2 standard deviation below the mean. Because the person that is 50, remove 70 from 50, give you minus 20, divide by 10, give you minus 2. So instead of now talking about talking about your unit, you say you are so kg, we talk about number of standard deviation away from the mean, which is the Z-score. That is how standard normal distribution comes. Standard, that is now universal, used in any field, engineering, medicine, social science, everything agree, any field. It's the same thing. So what did they do? They divided, they look at the difference between the value and the mean and divided by the standard deviation. That's what gave the Z-score. And that's what brings the standard normal distribution that have the area is 1, the standard deviation is 1. Everything about it is 1. So now, it's the same thing. Here, 2 variables vary together because of the unit issue. For it to be standardized, you now divide by the standard deviation of the 2 variables. So after you have calculated their covariance, you now divide by the standard deviation, it cancels out the unit. If you remember the case of the weight I gave you for the Z-score, if you say the person that is 90 is 20, you remove 70 from it, the difference is 20 kg. It's kg. The standard deviation you now divide by is kg also. So kg cancel kg. So it's a ratio. A ratio is what you get when you divide 2 quantity of the same unit. So it's now universal. It's the same thing here. So when you have 2 variables x and y, you calculate their covariance and now divided, you know, covariance, both of them carry the covariance, carry the value of the unit of x and y together. So if you now divide by the standard deviation carries the same unit. So the unit cancel out. In that case, it becomes a ratio. So when you now divide, look at it here. Correlation is standardized covariance. How do you standardize it? Correlation is covariance divided by standard deviation. So this is the covariance which we have seen before. Formula, the covariance. If you now divide by, this is the standard deviation, square root of s minus s bar square over n minus 1. Though the square root is also, the n minus 1 is okay. The n minus 1 is, you know, is still part of the square root anyway. It's the way to write it out very well. That is the problem. Now, this is just, this one is the, this is the standard deviation for x, this is standard deviation for y. So division, if by the time you change this one to times now, oh sorry, it's here, I've changed, I didn't change it. The times, yes. So when you change it to times, here, now the division change to times, of course the numerator will become the denominator. Change it like that. So you see that the n minus 1 here cancel square root, because this square root of n minus 1, square root of n minus 1 will give you n minus 1. So it cancel this n minus 1. So you cancel n minus 1 out of it. So it will now be this over this. And that is the formula for correlation. So correlation is covariance divided by the standard deviation of each variable. That's why, you know, when we were discussing during the initial lecture, we were discussing descriptive statistics, how to summarize quantitative variable. I made mention of something. Out of the, among the 3 measures of standard central tendency, mean, mode, and median, mean is the most important in the sense that it's the one that is more useful for advanced statistics. And when we talk about how do you calculate the measure of variability, we say deviation, because if you add deviation and give you 0, you square it. Then when you sum or square, Those are the things I was saying that are the things you see in advanced statistics. X minus S bar square, sum of square. When you are talking of ANOVA, that's what I think. If you run regression, run ANOVA, you see sum of square. Those are the things. This is the same thing I'm seeing here. So all you see is S minus S bar, Y minus Y bar, all over S minus S square. So all those things, that is correlation. So when you understand it from the basis, even from mean, standard deviation, simple, and variance, everything, anything you think about in advance is just around mean, standard deviation, variance, mean, standard deviation, variance, degree of freedom. That's all. So this is covariance. This is correlation, standardized covariance, and it can be written after some mathematical manipulation just to remove all those minus decimal out, because you try to remove this decimal will come in, just to remove it so that you can just estimate once and for all, it will give you the same value. But for you to understand it, just this the real formula, that is the origin of correlation. And it's dimensionless. It has no unit, as I've said it, because the unit have cancelled out. So correlation is not affected by changes in the, in the scale of measurement. It doesn't really matter. Now, I don't know if there's any question concerning that. So let's move further. Now, meaning of we have seen how it was derived from covariance. Let's look at, and the first person to describe it, even though the first person to coin the word correlation was Gartin, his student Carpesi was the one that described the derivation of covariance and correlation from covariance, and that is why that was called Pearson correlation coefficient. They also call it product moment coefficient. It's because it's about multiplying this and multiplying this. You see, the numerator is deviation of S minus the transdivision of Y, the addition of it, divided by the standard deviation of S, standard deviation of Y. So it's about product multiplying something between S and Y and dividing them. Now, the degree of linear association between the two variables is correlation. If you look at the picture of covariance we are looking at, it's the same thing as the correlation, is only that correlation is a standardized one. The strength of association is summarized by the correlation coefficient. So if you really look at covariance, it can take any value, based on this scale, depending on the scale of measurement. But the covariance, because you have standardized it for correlation, it has limited the value. It's now between 0 and 1. Then people say between -1 and +1. But to understand it mathematically, it's actually between 0 and 1. Because what it means is that the numerator can never be greater than the denominator. The numerator can be equal to the denominator. When the numerator is equal to the denominator, of course, it will be 1. But apart from that, even when it is less, it's 0 point something. So if it is 0, of course, everything will be 0. So from its numerator can be from 0 to 1. So the numerator can never be greater. Not 0 to 1 per se, but it can 0 to any value that cannot be greater than denominator. And that is why it cannot be greater than 1. So in between 0 and 1. But the sign is the direction. So if it's going to be negative correlation, it will have negative sign. Positive, that's positive sign. So maybe to describe, to actually explain the difference between this negative and positive, we go back to mathematics, because most of the thing in statistics is borrowed from mathematics. And though the people that develop statistics were not mathematicians anyway, they were not mathematicians, they were even professional like you, biologists, social scientists that needed it, they develop it. And in fact, if mathematicians are to teach you statistics, they will confuse you. Or the so-called people that made this profession, because they will just be writing S, just be solving. But the people that actually developed statistics were biologists and social scientists. Now, if you remember variation in mathematics, when you look at relationship between two variables, direct proportion and inverse proportion. When two things increases together, it's direct proportion. It increase or decrease together. When as one increase, the other one decrease, is the inverse proportion. So it's the same thing. Positive correlation is direct proportion. Negative correlation is inverse proportion. Another way of explaining it, since most of us are scientists, you know, we have done physics, some knowledge of physics and chemistry. You remember Sharp's law, Boyle's law. Sharp's law is direct proportion. Talk about the temperature and pressure of gas. As temperature increases, pressure increases. If temperature decreases, pressure decreases. That's direct proportion. That's positive correlation. As both of them increase together, if they increase together or decrease together, that's positive. So direct proportion, like Sharp's law, is positive correlation in statistics. But if you remember Boyle's law, as volume increases, pressure decreases, or volume decreases, pressure increases. So volume and pressure move in opposite direction, and that is Boyle's law. Inverse proportion, that is negative correlation. So in mathematics, what they call direct proportion is positive correlation. Inverse proportion is what statistics call negative correlation. A positive correlation is one in which both variables increases or decrease together. A negative correlation is one in which as one variable increases, the other decreases. When variables are exactly linearly related, the correlation coefficient equal either +1 or -1, depending on the direction. That is what they say now. If it's always all the time, as this one increase by this unit, and then this one will increase or decrease by this all the time, that shows that they are perfectly linearly related. So when you plot it, it will be on a straight line. We're going to see the graphs. Note that the correlation coefficient is unaffected by the unit of measurement. We have already said it because the origin of it, numerator and denominator, is the same unit. So it can cancel out. And that is why it's standard, like it's a ratio. It's the same thing like a z-score, odd ratio, relative risk. All those things are ratio. They don't have unit. So they are universal use in all the field because the unit of the underlying measure is already cancelled. The square of the correlation coefficient gives the proportion of the variation of one variable explained by the other. So this one, just to food for thought, we unravel it when we get to regression. And that is how correlation comes in regression, that last statement. So correlation coefficient R, which is this Pearson correlation coefficient we have just derived now. Well, you just use it. Every other correlation is like that anyway. Even either Pearson or Sperma or Kendall or whatever, is between -1 and +1. So look at the picture, pictorial view. Look at this first one. When they are always linearly related all the time, but if you plot it, it will be on a straight line. You plot all the value together, both of them will increase together on a straight line. If it's positive. If it's negative, that the one increase, the other one decrease, it will be on a straight line, negative. That will be the last one, -1. That's perfect negative correlation. This first one is perfect positive correlation. If somehow there are some scatter, look at this one when this to 0.9. It's not perfect, but they are still online. Look at this one, just creating a mental picture of what it will be if it is 0.9. Positive. This is second to the last. Negative if it is 0.9. The slope goes down. This third graph, if it is 0.5, how it will be positive. If it is going to be negative, look at the way it is. And if there is no correlation, look at the way it will scatter. In that case, the correlation is 0. So you cannot really say if one increase does not increase or one does not affect the increase of the other one. Everyone just move in their own direction. That is correlation 0. Now, let's talk about the coefficient. We already said the one we derive from covariance is Pearson product moment correlation coefficient. So there's an assumption that the variable being measured is at least on interval ratios, at least interval. When you say interval scale, it goes back to scale of measurement. So from here, I will pause. I keep on saying it, not because of it. Any of us that I want to encourage us, this thing I want to say, it will help me as a person, it will help you, it will help any other person also, maybe our friend that want to benefit from what we are doing. I want to encourage every one of us in this lecture, especially people that have not subscribed to, what do I call it? What we have done, normal lectures. It's just a token of subscription for a month or 6 months. It's a takeaway, something you can dash out. Please, I want everybody. Because some of the issues we'll be talking here, they are well explained. And in some situation, I don't want to be repeating myself. Or sometimes, if you have to explain it nitty-gritty like that, it will take some of our time. But they are explained there. And when you yourself, when you play those video, you yourself, you say, wow. I must say, when I play them, I just say they are the highlight of what we are doing. So I want everybody to subscribe to it. Now, the parametric, there's an assumption that Pearson product moment correlation is used in situation. There's an assumption that the underlying variable follow normal distribution. That is on at least interval scale. So I don't want to be talking about, when we say at least on interval ratio. So when we go and watch on scale of measurement under basic concept of statistics, go and watch it. We extensively discussed that. The Spearman rank correlation coefficient is non-parametric. In the situation where you have ordinal data, just like the one Dr. Balogun was raising, ordinal data. Well, sometimes if one variable is ordinal, one is continuous, you can still use Pearson. But when both of them are ordinal, recommend you use Spearman correlation. Kendall's correlation is the same thing with Spearman, but the only difference is that it is preferred when it's small, the sample size is very small, and there are a lot of tyrant. What I mean by tyrant, imagine you put something on a Likert scale, 1 to 5. You discover that majority, that 2 was the commonest among the response. 2. Maybe if the 2 is disagrees. So it's the commonest. In that case, we have a lot of tyrant. Now, point biserial correlation coefficient and biserial correlation coefficient. These two are very, very important. Point biserial, both of them look at correlation between a continuous variable and a dichotomous variable. Dichotomous variable means only two categories. So it's categorical variable, two categories, like male and female, dead or alive, yes or no. Admitted, not admitted. Think of any two things that diabetic, non-diabetic, obese, not obese. Dichotomous variable. But the difference between the point biserial and biserial is that the point biserial has to do with association between a continuous variable and a discrete dichotomous variable. While the other one, biserial, has to do with association between continuous variable and a continuous dichotomous variable. So there's a difference between discrete dichotomous variable and a continuous dichotomous variable. A discrete dichotomous variable is a variable that has no continuum underlying the two categories. That no continuum means that there is nothing like a number before they categorize them. It was not a derived variable from a number, like dead, alive, yes or no, in some situation, and male or female, admitted, not admitted. Those are discrete dichotomous variables. As opposed to continuous dichotomous variable like diabetic. Before you say somebody is diabetic, yes or no, you will have done a blood sugar and you now say blood sugar 126 and above, it's diabetic, the rest not diabetic. So there's a continuous dichotomous, there's an underlying continuum. So the two categories was a function of continuous variable number that you just have a cutoff. The same thing with anemia, with a PCV value less than or equal to, or hemoglobin concentration value less than or equal to something, you say somebody is anemic. The same thing is passing or failing exam. When somebody score above certain, you say it's pass. Somebody score below, you say it's fail. So passing or failing, there must be mark, there underline, there must be a cutoff. And that is where how a natural injustice coming. No. Somebody in medical school, somebody score 50, he pass. Another one score 49.9, fail. No, the difference between 49.9 and 50 will be maybe one step or the other. Just one thing. You know, maybe somebody allocating man refuse to allocate enough. So the same thing with somebody that high blood sugar 126 is diabetic, 127 is not diabetic, in 125 is not diabetic. So it's the same thing. So I don't know if that's the explanation of correlation coefficient. So even though the origin of correlation starts with Pearson, but after some time, intelligent people have come with Spearman, Kendall. We are going to see how they derive them and solve some of them and run the analysis point by serial and by serial. This is Pearson, this is Spearman. Then we can look at, before we look at an example, I don't know if there's any question. So let's look at an example so that we look at how each, you can actually, we look at the example for each of them, at least for each of the three. Any question? Any question? No question. We should proceed, right? Okay. If you have question, you can shout it. If you want to talk, no question is stupid. So if you don't want, you can shout it to me privately. I will just read the question and answer. I will not say the person that shouted it. Now, let's look at an example. There is this case of 15 children trying to look at their height in centimeter and their pulmonary dead space, the part of the respiratory tract not used for gaseous exchange. Now, the dead space measured in mil, the height in centimeter. So from what we have just said now, look at how we derive, we have derived the correlation, first correlation. This is the formula. This is a standardized covariance. All you need to do is to know what is the deviation, the difference between mean of the value and each value. So the sum of height is here. This is sum of height, 1,269. This is the mean height, 144.6. This is sum of the pulmonary dead space, 1,004, and the mean is 66.933. So you can easily use the mean to know the deviation for each of them. Look at the deviation of y. So you can multiply the two with deviation. When you multiply this and this, give you this. Then, since in the formula also we are looking at their standard deviation, you can square each x minus x bar and y minus y bar. You can scale them and add them together. When you add them together, you Yes. You add them together, if you look at it here, you're going to be talking of, say, you are dividing because you know the n has already cancelled. Where both the covariance and the standard deviation have that sample size n minus 1. They already cancelled. So all you need here is the square root of this. Square root of all this, which we have calculated here. Look at the square root. This is sum. This is square root of this x minus s bar and y minus y bar. So the formula, look at it. S minus s bar times y minus y bar, which is the numerator. Addition of it is this 5426.6. That's the numerator. Then the square root of s minus s bar square, the summation of it, look at it here. For y is this. So when you do this, you will slot in the correlation is 0.846. Any question? Very straightforward. So I know that there's no question for that because it's very straightforward. Let's run it because we have the data. As everybody has the data set. Let's run it. Who will share with us? Who will share the data? Somebody should share. Is height and pulmonary dead space. That's the name of the. So, Dr. Additional. Dr. Additional.
Hello, sir.
I assume that you have.
Hello, sir.
Yes, I
No,
assume that
I don't.
Are you on?
I don't now.
Oh, are you on?
No, I'm on a phone.
Oh, okay.
Yes, I'm on the move.
Oh, you're on the move. Okay.
Yes, but I'll soon settle down.
Okay, no problem.
I'm following you very well.
Okay,
I'll follow you very well.
Drive safely. Concentrate on your driving.
Somebody's driving me.
Okay, that's
Somebody's
great.
driving me.
Okay, that's great.
Somebody's driving.
Okay.
Okay, sir.
Yes.
Yes,
Okay,
sir.
who will share with us? Who will share for us? Who will share? Dr. Babagana has not joined us. Who will share? Where's my phone?
Dr. Dagbo,
Yes, sir.
which
Yes, sir.
data set are we using?
That is height and pulmonary dead space.
Sir?
Height and pulmonary dead space. Height and pulmonary dead space. Height and pulmonary dead space. So you are trying to share, right? Somebody is sharing. Ugo, you can share if you want.
No, because I knew that there were new people coming, so I just didn't. It's just now I'm even trying to open that other laptop that I used to share.
Because
Like,
I don't
that
want to be doing the sharing. Listen, if I do the talking, I should not do the sharing.
I don't mind doing it. It's just that I did not know that. I thought that maybe the new people, since like this is their main. I don't want to take away.
Dr. Bagara, you are not joining us. You have started. Okay, no problem. Okay, no problem. Yeah. Okay. Okay, welcome. You can share. Okay, thank you. You can share. Or you like share? Yeah. Dr. Aoyemi, are you trying to share? Hello? Because this sharing of a thing, it will give us the opportunity, give people opportunity to learn this thing, to be part of it, make it stick. So not that I can easily do it. So but just for other people to benefit.
I'll soon share.
Okay, sir.
I'm going to share.
Okay,
let me just down.
Okay. let me just share here so that next one share. Can you have it? This is you can see this is the data set, the height in meter and pulmonary dead space in mil. So it's very simple. We want to do the person correlation. But it doesn't really matter. Even what the correlation, they are in the same place anyway. We go to analyze. Analyze, correlate, bivariate. So I'll come and explain this bivariate later. You just move both of them. Yes, you move both of them inside. If you look at by default, it's Pearson correlation that is checked there. We have Kendall, we have Sperma, but they just paste the Pearson now. Click OK. Let me share the results.
Sorry, sir, my network misbehaved.
No problem, no problem. That's why I could. Look, can we see the result? So the way it does it is that it arranges in a matrix. You know, if you look at it, height and pulmonary dead space, height and pulmonary dead horizontal. So this first one intersection will be where height correlates with height. It will be 1. Then this one will be where height correlates with pulmonary dead space, which is 0.846. If you go here, pulmonary dead space correlates with height, 0.846. It's the same thing. Why pulmonary dead space correlates with pulmonary dead space? 1. So the where both of them correlate with each other, one and with themselves, it will be along the diagonal. It will be 1. Why off the diagonal is so in this case now it's just only 1 correlation because there are only 2 variables. So it's the same. You see. That is what we calculated with hand, 0.846. But what you could not calculate with hand, so we can show the way if you want to see if it's significant. In the next slide, I will show you can use t-test to check if the correlation is significant. So here, the p-value is written here also. So the p-value is less than 0.001. It shows that it's significant. We are going to see later, because in interpreting correlation, the p-value is not useful in the sense that the p-value depends on the sample size. A small correlation, if the sample size is large, it will be significant. The p-value will be significant. A big correlation, if the sample size is very small, may not be significant. So that is why sample size, the p-value for interpreting correlation is not the best. It's not useful. So that is why intelligent people have devised a way of interpreting correlation. So we're going to see in the last part of our presentation today, we look at that, how we interpret. When will you say is okay, is big enough? So just forget about p-value when it comes to correlation. It has no place. Any question concerning that? Okay.
Hello, sir.
Yes, sir.
Hello, sir. I think
I'm
I have
listening.
a question concerning that.
Yeah, I'm listening.
For p-value, you said it's not significant concerning correlation.
No, I'm not saying it's not significant. I said that this one is significant, but it's not useful.
You said it's not useful. You said it's not useful in the interpretation.
Yes.
But some people also say that when you have a R coefficient that is low, like, when you have 0.1, it ranges between, like you said, it ranges between 0 and 1. Mm-hmm. So when you have the low ones, that a p-value that is significant actually shows that there is no relationship. And that the fact that there's no relationship is significant. See what I'm saying? That if a correlation is between 0.1 and like 0.2, that means when the correlation coefficient is very small. We say correlation coefficient ranges between 0 and 1. Mm-hmm. So when it is very small and the p-value is significant, then it actually shows that there is no relationship between the two variables that you are trying to study.
Okay, if
You understand? So I just want you to throw.
yes, if that is the case, so what if it is very low
You,
and it's not significant? So it doesn't mean there's a relationship.
okay.
If the correlation is very low and it's not significant, does it mean that there's a relationship?
No, it does. Well, and there's no p-value. Okay.
No, what
That's
I'm saying is that
so
it can
okay.
be low and you
That's a
see,
good
and
argument.
when and it's not significant, does
No,
it mean?
I understand you. And I understand what you're saying, sir. That's what I'm saying. That okay, that I get your argument. That okay, it is very low, but the p-value is not significant. So how do you interpret that? That's what you're saying now.
So we have already said
Hello.
that you're going to see later. Don't
Hello.
worry. By the time you get to know him more, even when we do regression, because the correlation has a place in regression, in interpreting regression also. It has a place. So somebody, this last lecture we just give on correlation on Tuesday, somebody shared something with me that we were doing the lecture, the analysis she did, she wanted to public, and we were just looking at it. So you will get to know that sometimes when the correlation is very small, you interpret, I talk about R square. If you square the correlation coefficient, it's actually telling you the percentage. If you are trying to compare two relationship between two variables, of course you can say, even though in correlation we say there's nothing like, it's just a crude way of saying there's nothing like dependent or independent. Doesn't mean that there's some variable that is independent when you are correlating two variables. When you're talking about the income, family income, and spending and spending, there is a correlation between level of income and spending on maybe things that are luxury goods. So that one depends on the other. The spending on luxury goods will depend on the income. So when you see correlation, when you square the value of correlation, it gives you an idea of how much of that particular outcome variable is explained by the exposure variable by squaring the correlation coefficient. So sometimes when something is low and you square something, is even give you less than 1%. If less than 1% of the outcome is due to this, why you bother yourself? So that is why, and the correlation can be the p-value can be significant because the sample size is very large. If the sample size is very large, the p-value is, so that is the drawback of that. And you get to know if you go and listen to the initial lecture we are giving on introduction to inferential statistics, you even get to know in medicine, people do even apart from this issue of correlation, p-value, they don't want to hear. If you want to publish in Lancet, they don't want to hear p-value from you. They don't want to talk about p-value. They prefer confidence interval.
Confidence interval.
Yes,
confidence
because
interval.
they will tell you that this p-value has no place in medicine. It started with agricultural research in the early 19th, where they dichotomized study into significant and non-significant. It has no place in medicine. That's what they will tell you. So we'll move further. You see, I've already explained the reason p-value has no place in that correlation because it's grossly affected by sample size. A small correlation, big sample size will be significant. A big correlation, small sample size may not be significant. So it doesn't give you the triple. A p-value does not solve the problem, and that's why the intelligent people, they have devised a way of solving it. So I think we'll move forward. Let's look at so let's move forward and look at the next thing. So now, just like what we say, if you want to know for the person correlation, if you want to test the correlation, the significance with ant, you use t-test, and this is the formula. Even though it's not useful, but for academic purpose, this formula. And if you run regression, you get the same value. Now, as I already said also, you can actually say correlation is part of regression because when you run regression, correlation also feature there. So when you run regression, this T comes out. If I want to now calculate, maybe I want to run, or to do the T with correlation, I will, if after running the correlation, if I want to know the corresponding T, I just run it as regression. If I run the data as regression, it brings out the T. Run with SPSS, it bring out the T. Now, let's look at the Spearman rank correlation. What we have just solved now is Pearson moment, product moment correlation. Let's look at Spearman rank correlation. In Spearman, what you just do is a plot of data may reveal outline point when and from the main body of data which will really influence the calculation of the correlation function. That is, when there are some outlier, even though if that particular variable normally follow normal distribution, if there are some outlier, that particular data test set may not follow normal distribution. So alternatively, variable may be no quantitative district, such as count, a number of children. So that one you cannot say is a continuous variable. Though it's numerical, but it's discrete, numerical discrete. Other categorical such as Likert scale, like pain score, like all those severe, moderately severe, mind or whatever, all those Likert scale, it's better you use Spearman rank correlation. It's a non-parametric procedure. Is to replace the observation by, instead of you will see the way we calculated the person, you actually use the value. No, you remove the mean from each value and calculate it. But in Spearman, just like any non-parametric statistic, you don't actually make use of the real value. You rank the value and then make use of the rank. It's the same thing here. So let's look at the same data set. The same data set we use, this height and pulmonary death space. Let's look at it. Let's use Spearman to do it. So you have to rank the two. So you can arrange the first variable, the rank, according to the way the rank is. So height, if you look at it in the height, the way we arrange it is according to smaller to, so the rank is 1 to 15. But the second one, you rank it beside. If you arrange the first one according to the way from smaller to the highest, you cannot arrange the second one like that. Because if you try, you cannot, both of them, they don't concise. So, but it doesn't mean that you cannot rank it. Arranging is different from ranking. Even the first one, we can rank it without arranging it. We can scatter it and still give the rank. It's just a matter of putting the smallest one to be what, the highest one to be the highest number. That's all. So, like this one now, look at the pulmonary death space. The smallest one is 31, that is ranked as 1. The next one is 43, is ranked as 2. The next one is 44, is ranked as 3. The next one is 45, is ranked as 4. The next one is 56, there are 2 of them, 56, 56. So each of them is supposed to be 5 and 6. Because they are the same, that's the way you rank. You have to now add, both of them have rank 5 and 6 now, because 56, number 5 and 6. So you now add 5 and 6, making 11 divided by 2, making 5.5. So each of them will be 5.5. You divide it among themselves. In that case, there won't be rank 6. So the next one now will be rank 7, this 57. The next one is 58, rank 8. The next one is 64, rank 9. The next one is 78, rank 10. The next one is 79, rank 11. The next one is 88, rank 12. The next one is 92, rank 13. The next one is 101, rank 14. And the last one, 112. The highest one, 112, rank 15. So all you need to do is that you can see the 2 ranks now, side by side. You find the difference in the rank. You remove, it doesn't really matter whether you remove the first one from the second one, the second one for the first one. It doesn't really matter. This doesn't mean that it's just remove one from the other. So when you do that, you give it a value. Now square it. Why it doesn't really matter which one you remove is that whether it gives you negative or positive, when you square it, the negative come out. So it's the d square, the different square we are using. When you square it, you now add it together. So for this data set now, the addition of the square is 60.5. So the formula for the rank correlation is 1 minus C sigma d square over n into n square minus 1. The only thing you are looking for here that is not constant here is that d square. Because the rest, the sample size, that's the only other thing that is there. The sample size, you already know the sample size. So that's the only thing that is there. So just put in and calculate 0.892. So you remember the corresponding Pearson correlation is 0.846. But the Spearman is a little bit bigger, 0.892. So let's do the running. Let me go and run it now. Go to the same data set. I think you can see now, analyze, the same correlate, it's the same thing. So let's click on Spearman. Like this now. So it's both Spearman and the first one is Pearson. Look at the Spearman. So that is what we got, 0.892. That's the correlation. Any question? Any question? All these things for us to have the mental picture of how it works. The most important thing for you to know how you can use your machine, your computer to run it. There are all these things for us to understand the logic. When you understand the logic, make the interpretation interesting. Any question? No question. Sorry, I just went out. They just disconnected. Any question? No question, right? Okay, let's move forward. So let's look at Kendall. Kendall has a different approach, and the way they approach is that they look at when they try to rank, after ranking and also the situation also looks slightly different. Kendall is most useful, especially in a situation where maybe two different people rank. If you look at the other one we just did, there are two data sets that they have their value. But in this case now, most of the time, if two different people rank a group of people, like this one now, this data set you have here, you have a director and a manager who ran those people that came for interview. About 12 people came for interview in their institution. So based on the performance they recorded, manager ran somebody number one, the second person, arrange them according to the way he ranked them. While the manager has his own slightly different. These are the two they rank. So this is the first one is the rank of the director. This is the rank of the manager. So the person director rank number one, manager rank the person number two. And the person director rank number two, manager rank number one. And some other changes also. Some places. We want to see, but the fact that there are some slight change doesn't mean that the rank, you cannot say the rank don't correlate. So you want to, do they actually correlate? So the logic they use here is this kind of tout, there are three types. We have kind of tout A, tout B, tout C. The one that is commonly used is tout B, and that is what you also have in all the what do I call it? Software, and that's what we are calculating here. So, and the logic behind is to look for what they call concordant and discordant. For each level, so when you first of all arrange the first ranking, then you look at the second ranking against the first. In looking at the second ranking against the first, we want to know for this first one, for this second ranking, this first one, how many on the other side are concordant? The concordants are any value that are above that value you are looking at. The concordants are values that are above that value in the opposite direction. While the discordants are the value that are equal to or below the value in the opposite, in the other rank. So like now, for this one now, this first one now, that is 2. So hello? So for this first one that is 2, if you look at this below, from below it on the other side, how many are above that 2, the rank? If you look at it, all of them except this one, that number 1 that is equal to it. So you know from here down, there are 11 of them that remain because everything is 12. But we are looking at below this 2. From here down, from below there are 11, but one of them is not above. So there are 10 that are above. That's why the concordant is 10. When you move to this one, from these 3 down, there are 10 of them, and all of them are above that one. That is concordant is 10. For these 4 now, there are 9 of them below, but that 4 is not above it. So the remaining one that are above it are 8 in number, and that is why it is 8. For these 3, from these 5 down, they are above these 3, and they are 8. For these 6, we have 7 of them down, but this 6 is only 6 out of the 7 that are above this 6. So that's why 6. For this one, this 5, all the 6 of them that are below are above it. That's why it 6. For this 8 now, this 8, you see that all of there are 5 of them. All of them are above except this 8. So there are 4 of them that are above. That's why it's 4. For this 7, all the 4 that are below are more than 7. So that's why it's 4. For this 10 now, it's only this 11 and 12 that are above the 10. That's why it's 2. For this 9, it's only, of course, it's the 2, 11 and 12 are above. That's why it's 2. For this 12, there's no one. Because only 12 that is here, and it's not above this 12. So that's why it is 0. So when you finish with concordance, in discordance now, you are looking at the same thing down, but how many are below or equal to? If you look at it, only these 2, from here down, only these 2 is equal to these 2. That is why it's 1. Here, from here down, there's no one that's below or equal to 1. So that is why it's 0. From this one, it's only this 4 that is equal to this 4. Or below it. So that's why it's 1. Here, there's no one that is below 3 from here. That's why it's 0 here. For this one, it's only this 6 that is equal to, that's why it's 1. Then from here, there's no one that is below 5. That's why it's 0. This one is only this 8 that is equal to 8 or below. That's why it's 1. Here, there's no one that is below 7. That's why it's 0. Here, only this 10 is equal to this 10. Only 1. That's why it's 1. Here, there's no one that is below 9. That's why it's 0. Here, this 12, only this 1 is equal to this. So you can have a discordant now. So you now have the concordant, everything is 60. You have the discordant, 6. And the formula is concordant C minus discordant all over concordant plus discordant. It looks much like a formula for Mach-Nehmer chi-square. But in Mach-Nehmer, is concordant minus discordant square over. No, that one is not concordant minus discordant. Is the 2 concordants, discordant rather. The difference between the discordant square over addition of the discordant. But this one, concordant minus discordant over discordant minus concordant plus discordant. So 60 minus 6 over 60 plus 6, making 54 over 66, 0.181. 0.818. Any question? So actually you can revise it. There's no big deal here. And if it gives you a problem, just discard it. Doesn't just know that it's ranking for some situation you use it, and the computer will run it for you. So let's run it. Somebody to share, you see director, manager ranking. So let's run it. That data is there. Director, manager ranking. I hope the AC is too code for me. Director, manager, who is sharing? Nobody is answering. Dr. Adeshina, are you settled now?
My system is not working. I mean, I'm using my phone.
Let me share then.
It's my phone I'm using.
You are using your phone, okay. Okay. Let me share. Let me look for it.
I have my system in front of me anyway.
Okay, no problem. I think it's director, manager ranking. That is the yes, manager ranking. Yes. So I don't know if you can see it now. You can see the data set. Can everybody see it? Please answer me, please.
Yes, sir.
Okay. So
yes, I can see the data set.
Okay.
This is Dr. Adeshina talking.
Yes,
okay,
sir.
that's
Yes,
it.
sir.
Okay. Analyze is still the same correlate.
Correlate, yes. Yes. Then you take.
So let's look at Kendo. Kendo we are looking at. Let us let me share the output. Can we see it? 0.818. That was what we calculated with time.
Yes, sir.
Yes.
Yes, it's as simple as that.
Yes.
Very simple, very straightforward. So that is the correlation. Though we will quickly look at some other things about correlation. Correlation looks simple, but there are a lot of things underneath. We talk about point biserial and biserial. Though theoretically they talk about this formula, but I don't see how it works. But the good thing about it is when you do your piercing, your piercing, if you know the biserial point biserial is a correlation between a continuous variable and dichotomous. So when you do your piercing, it gives you, that is the point biserial. Is the
excuse me, sir. Excuse me, sir.
Yes, sir.
Excuse me, sir.
I'm listening.
Please, I want you to really differentiate the point biserial from the biserial very well. Okay. I saw I understand your differentiation, but which one is point biserial and which one is biserial?
Point biserial is the one that there is two categories, but there is no underlying continuum, like sex now, male and female.
Okay, sir.
Okay,
thank you very much, sir. I got.
That's point.
Yes, yes, I now got that. Yes.
Okay.
Points. Okay.
The biserial is the other one that maybe due to you do blood sugar.
You have a number.
Yeah, there's a number.
Yes, diabetes and things like that. Okay. Yes.
Okay.
Okay. Thank you very much, sir.
Okay, welcome. So just discuss this one, but because the expresses bring it out. All this one, a proportion of cases that fall into. I don't really see how it works because you can describe that for the dichotomous, what of the continuous variable aspect. So the continuous, anytime you are using categorical variable for correlation or regression, it has to be coded 1010. So if this issue of point biserial or biserial, whatever, Since there are two categories, one category has to be coded 1, another one 0. I think this is where Dr. Ikoba was raising issue because that you are creating dummy. So Dr. Ikoba was raising issue on
let's use
Thursday.
SPSS.
Yes, I will do that. I will do that now. How to create the dummy. I will do that now. I will just share.
Okay.
So I would even love you if you have a data to share. Who has a particular data that has both babies? There is sex there, there is age there. Simple. Who has a data to share? Nobody. Nobody want to share. Let me just share a particular data set here. Let me share a particular data set you can use. I just use it.
So the computer that has my data is not charged.
It's not charged.
Tomorrow I'll be ready for it, for sharing.
Okay. Yeah, okay, no problem. Let me just do for a data set here. So that we even do the bacteria and point bacteria. We first of all do the dummy. We create the dummy. What data set has this one here? Yes. This socio-economic class.
Can I just share one?
Yes. Okay, you want to? Okay, that's good. Well, share. Share, sir. Share. No.
Can you see me?
Okay. But, I can see it's in Excel, right?
Yes, I can see your screen. Dr. Larry, I can see your screen.
Yes.
Okay.
It's in
Your screen is an Excel. You are sharing an Excel screen.
Is it Excel you are sharing for us?
It's in Excel.
But want you to open your SPSS and bring it into SPSS. What you can do, first of all, open SPSS, then you go and look for it. I mean, let you learn that one. So because you want to do this.
Okay.
No, we can do the code here in Excel. Or you want us to do it, it's good. I want us to know how to do. In Excel, it's very simple to do the coding. All you need to do, if you say, all you need to do is to.
You can take. I think you should take my stuff, Dr. Lapo. I need to.
What is it?
I need to look at your SPSS.
No, what you need to do, you open SPSS first. When you open SPSS, now from SPSS, go and read this Excel. Open SPSS first. Open SPSS before you share. Because if you don't
I have my SPSS.
Yes, come out of
I have it.
What is it?
Stop sharing.
So
let me look for my SPSS.
Come out of sharing. Stop sharing your screen.
Stop sharing.
Okay. Yes. So now go to SPSS.
Okay.
Go to SPSS. Go and do SPSS. When you open SPSS first, you now share the SPSS. At least even before you go and look for those files, you make sure it open first. When it open, you now share. You now go and share the SPSS for us to see. We can now guide you how to go to where you can look at it. Look for the Excel. You know where you save the Excel?
I'm trying to locate. Okay. No. Sorry, share the one you have. I will come to it back to it.
No problem. Let me share. So you can see. Can you see? Can you see the data? If you can see, let somebody talk, please.
Yes, we can see the data. I can see the data.
So this
yes,
data
sir, we
set,
can, sir.
Yeah, you can see this data set as age. This is this data set socioeconomic status we use in
it has age.
chi-square. We use in our proportion chi-square class. We have age, we have sex. the examiner.
Okay.
And we coded the
employed
yes,
education.
So age is serving as our continuous variable now. We want to use sex as our, even employment also. Let's just use sex as our point by Syria. We want to code sex. How do we code it? 1 and 0. It's already coded 1 and 2 here. So if you want to know how it is coded, you can go to variable view. Look at this.
Variable view.
The 1 is male, 2 is female. So if we want to do create dummy for it now. So you have to make up your mind which one do you want to use as a reference. So the logic behind it is that if you are analyzing, let's say now, the attribute you are looking for is higher in male than female. Are you listening? So you use female as your reference if it's higher in male than female. But if the attribute is higher, you have done your initial analysis, the attribute is higher among female, it's good to use male as reference so that it is easy for you to say how many times is male more likely to have it than female. Like now, I will do this one, I will even go and read that lady's work. The lady that I shared the work on the peak expirative flow rate. The peak expirative flow rate was higher among male. So when I was I coded, I did the dummy for sex. I used male as 1, female as 0 because I know that the thing is higher among male. So though if I do it otherwise, give you the same answer but in different way, it may be difficult for you to interpret. So let's just assume, just an assumption. Let's just make, okay, let's make male, maybe female 1. Okay, let's make, okay, choose. I want somebody to choose. Which one should we use as 1? Which one should we use as reference? I want you to just say something. So I'll just do
female as 1. Female as 1.
Okay, so male is a reference now. So male will be 0. So and okay. Because what you need to do is just go to data. Dr. Ekobo, are you following? You go to data.
I'm following.
You click on data. When you click on data, you go to select cases. That's the second to the last option there. Select cases. When you click on select cases, you now bring that. By default, you see all cases. You now click on if condition is satisfied. Immediately you click on it. The if under it will be highlighted. You click on the if. It now give you this keyboard. You now move sex inside. So you want to, you have to know the way you enter the sex there. We have entered male as 1 and female as 2. They want to make female as the 1 now. So we want to select female. So we now say equal to 2 because it's 2. I say select sex is called 2. It's like saying I'm selecting female because female we coded 2. Immediately you do that, just say continue. Okay. So if I go to, let me share the data editor window for you. You will see by default, if you look at your bar here, beside at the left side, you see that it has crossed out all the male. It crossed out the male. It's only the female it didn't cross out. That one way. If you look at the last variable there, it's a filter. Can you see? That filter. That like all the male, it has that it cross out, it puts 0, 0, 0 for them. All the female, it put 1, 1, 1 for them. Can you see? All those male, the one that are 0, they are male, cross them out. It has selected only the female. But you are creating a variable, a dummy variable. So it's not just select, because this procedure is used for 2 things: to select and to create a new variable. So if you now want to name your variable, go to variable view. You see that filter there. Can you see? You now change the filter to I can call it female sex, or female dummy. Why I don't want to call it sex dummy is that calling it female dummy tells you that I've coded female 1, male 0. That dummy is for female. If I want to create male dummy, I will change it. I'll select male. I'll call it male dummy. So you can remove this. You remove this one.
So the female dummy in this case means that your male was reference value.
Exactly.
Okay.
The male is reference. Female is the one that is coded 1. So the select, the 0, you're renaming. It doesn't change anything, but for you to rename it, to make it aesthetic to you. Not selected, that is, you just call it no. You change it. Selected, you call it may. Or on the yes, rather. Yes. So, female dummy, yes or no? Yes mean 1, that is the female. No mean it's a male. Simple. So, when you finish, don't forget to go back to your data and go to select and say all cases. Just say all cases. So, because if you don't go and do that, when you are running the analysis, only the female that will bring it because it has cancelled out the male for you. But when you go back all cases, it has opened, but it has created, you have created a new variable, a dummy variable. If you go to data editor window, look at it, in data editor window, you can see, can you see female dummy? Can you see? Can you see the variable female dummy? Is there. That's how to create dummy variables, sir.
Dr. Odolapo, I'm just wondering, rather than go to true select cases, if you try to record and allot 0 and 1 directly without having to go through that step, will it work?
Yeah, it will work, but 2 things. It's the longest journey. 2 things. You have to now select it, all those 1. The same way you now, like this one now. I have to now say select.
Before.
Are you following me?
Yes.
I will now say select ascending, sort ascending. When I sort, I will now put 0 and replace this 1, which is male, is 0. I will now copy it and now drag and paste on all the 1, which is the male. Yes, and paste 0 on them. And now do the same thing for male, female. I will now put 1. Because it is female, which is the 2 here. I want it 1. I want the other one 0. Yes, I mean now. That is, so you can use it longer, and you can make mistake. You can, by try to page, you can go and paste something, overlap or another thing. That is 1. Another is that you may want to still retain the original the way it is, because why I like, you know, sometimes when you are entering your data, if you already know the type of analysis you are doing, you can code it accordingly. Exactly, some questions are yes or no. If you know you go to do maybe all this regression, you can say yes is 1, no is 0. But the problem with that is that when you are running your analysis, it can confuse you, because especially if you want to something like sensitivity and specificity, you want to do it. In sensitivity and specificity, or even not only that one, if you are calculating odd ratio out from the 2 by 2 table, you want to use star card to do it, apart from sensitivity and specificity. That set 2 by 2 table, A, B, C, D, each of them have their what they mean. I don't know if you understand. Let me share, let me just demonstrate what I'm saying. When you have table, 2 by 2 table like this, you know, now, so when you say A, B, C, D rather, You know, this is A plus B, the total here.
Plus B. Yes.
Capital. C plus D.
D. Yes.
This is C plus A plus C.
A plus C.
And this is B plus D.
And B plus D. Yes.
So if you are talking of sensitivity now, A is the sensitivity, D is the specificity. This is A is false, is true positive, D is true negative.
True positive.
This one, true no, D is true negative, B is false positive, false positive, C is false negative. So each of them, they have designation. Yes, I'm now. So if you go and code 1 and a 0, whereas 1, your own is what you think should be A. The 0 should be B. But because alphabetically the 0 comes before 1, it will swap it. That is why when you are coding, you will still prefer coding 1, 2. A, the attribute A will be 1, this one will be 2. This one will be 1, this one will be 2. I don't know if you understand now. If you go and code AO for that thing, it will swap your this thing. Put this one B here and put D here. So you may be confused. If you are calculating all the ratios, also you get confused. And that is why it's still good when you are doing your coding to code it 1 and 2. Yes or no, make it 1 and 2. 1 and 2, because 1 will come before 2. And you want your yes to come before no. I don't know if you're, because yes, disease, no disease. No, treated, not treated. So you want it to follow in that way. 1, 2, 1, 2, rather than 1, 0. But if you now want to code to, you now create them, if you want to now do regression with the categorical variable, create another one which will be the dummy. That is the convention I'll be using, because else you can just run analysis, you are telling like, you don't even know, you just use everything just move together and you can't see the head or tail. I don't know if it makes sense. Dr. Balogun.
So I didn't understand that last explanation.
Which explanation?
Hello.
I'm still trying to. Let me just.
Hello, sir. Hello, sir.
Okay, 3 people
Hello,
want to
sir.
answer. 3 people are talking one by one. Please, I will attend to all of you. Go on. Who is talking? Yes, go on.
Can I go ahead, sir?
Go ahead.
Yeah, this is Dr. Additional.
Okay, I know.
Yes, I think what Dr. Balogun is saying is that the same way you created that dummy table, we can just create a dummy table from our initial variable by using record variable as a record as a different variable.
Yeah.
So if you record as a different variable,
is what I did now. No,
variable.
No, that's not what he.
No, you went to
through select cases.
That was what he was saying, sir.
Because you can do record into different variables twice. It will open a new column for you each time.
Okay, okay. Maybe I will ask you to do it, because that particular record is for different thing. It's for different thing entirely. I don't know if you understand me. It's for different thing. Maybe okay, share.
Damilola.
I want you to share and do it, because that record is under compute. It is when you have continuous variable, you want to have different. You want to now range it. You want to range it to more than 3. Though you can use to range to more than 2 categories.
I'm in a meeting, so I can't answer.
Okay.
So, I don't know if you understand me. So that one is for different things. So if let's say you can share, and I want you to share to do it to demonstrate what you are saying. Because let
me see. I think
demonstrate what you are saying. So in fact, the best way to do it is to go and do that select.
Let me open this data, sir.
Okay.
Okay. Now this one has gender and age.
Which version is your SPSS?
2023.
Okay, that's great. Okay.
So, like this one now, I don't think I've coded.
Okay, do that for gender, and you say you want to recode it because the gender is the this data has everything we are looking for. If let's say you are showing this one to us before.
Let me see transform code into different variables.
It will work. Dr. Tunde, this one will not work for gender. Okay, try it. Gender will not. Try it. Gender will not move.
No, I'm not going. Let him be doing it. Coded anything here.
Because
this
you know,
just like
gender
is, I don't think
yes, you enter gender as a string variable, so I don't think it will.
No, even okay. Listen, we can even go. Listen to me. You can even go back and enter gender as a numeric. No problem. You know what?
Numerical.
If you want to do it as numeric, sort that gender now. Sort it. Right click. Right click. Just right click where you are. You have moved. You have deleted though. Undo. You have deleted gender out.
Undo. You have deleted
undo,
gender. Yes,
right click. Right click. You click on clear. Don't click on clear. Right click and click on ascending. Sort ascending. Yes. Sort ascending. Now, you know, F will come first. So what do you want to code? You can code female as 1 and male as 2. Yeah, do that. That's not what we are saying. No. Listen. Wait.
No.
Okay.
Dr. Balogun, that's all what I say. You know, that's not what I'm asking you to do. Now, what you're going to do is that click on that first F. Click on that first F. Then remove it and put 0, put 1 there. Maybe you want 1 to be female. 1. Put 1. So click on it now. Copy. Right click. Copy. Not cut. Yeah. No, you have to right click. Copy. Select all of them. This F now. No, the F only from the second F. Just select down. Right click. Right click. Paste. So this one, male now. Come back to the M. Come down to the second, the M. Come down, M. Yeah, type 2. Type 2. Type 2 there. Then come out of it. If you not take, come out of it first. And go back there. Right click. Copy. Then select everything down to where the hem ends. Right click and paste. So now go to your variable view. Click on your variable view. Okay, go to your label. Yes. Go first of all. Go. You can go to string now. To you. Okay, you can label first. Doesn't matter. 1. Click. Put 1. Type 1. Are you not there, Dr. Balogun? Type 1. Hello, can somebody hear me?
Yeah, I can hear you.
Hello.
Maybe it's not network.
Yes, I can hear you. Maybe his network is
gone.
I think it's floating. It has gone. Okay.
His network has gone. That's why he's hanging. You cannot hear. Okay. So if you see that he's out. He's out. He will join us. So, Dr. Adesina.
Sir.
What I was telling you is that by the time he finished that one now, you cannot do that recode into this thing. You use it when you want to collapse continuous variable into categorical. Do you get the picture now? Yes.
Yes,
So
yes.
what I want you to do, even if you want to even do it for maybe blood sugar, you want to dichotomize it, make it into 2. If that just selects the fastest way, just go select. When you just say select, even if it is blood sugar, just say blood sugar greater than equal to 126. Okay. So you just go and it has created a new variable for you. You just go and rename the variable because we use the filter. You go and change the filter to the name of the variable. That's all.
Okay.
So
okay,
that's
sir.
just it. That was why I was asking him to, well, when he was talking, I knew what he was saying. So, Doctor, when he joined us, we'll continue with him. Dr. Ikobo. Dr. Ikobo.
Sorry, I'm sorry about that break in
Yeah, we know that
transmission.
the network took you out.
The network, my network. Okay.
Dr. Balugia, welcome back, sir.
Yeah, sorry about it. Let me see if I can share
Okay,
again.
share so that I continue. Dr. Ikobo.
Yeah.
I think you are following
I can hear you
now.
Okay.
I followed what you have done, except that that area where you said that we can convert the blood sugar to diabetic and non-diabetic.
Okay, that we do
that
that
last
one.
part of it,
It's even good for you
what
to share your own stuff also. All these things, it's better you are part of it live. So you want to change to numeric.
I'm back.
Yes. Click on numeric. You want to change that thing to numeric. Click on numeric. No. Yes. Yes. Okay. Click OK. Click OK. Yes. So go back to the value. You want to change the value. You want to label the value now. In front of gender. The value. In front of gender. The column in front of gender. After label.
Value label. Okay.
Value. The next column after label. Go back to data, the variable view. Variable view. Because if you don't do that, you forget what is
I am
one.
there. Okay.
Yes. Yeah, put 1. Type 1 now. Type 1.
Value. Okay. So 1 in this case would be
female.
Confused.
Female now. In female you 2 as 1. Yes.
It will be female.
Female, yes. Add.
Forget, I think.
2. Male.
Male.
Okay. Now you have done that. So go to that your transform. That thing say you wanted to do. Let's see how you want to transform, because you want to now transform. Maybe you want to transform female to 1 and male to 0. How do you do that here?
We can give. It's not going to work.
You can give a new name.
That's what I'm telling you. So just
you can give that.
No,
you can give
go
that
ahead.
same name.
Go ahead. Put it as gender.
Go ahead. You can do female. You can do female dummy.
Call it anything.
You just do female dummy.
There is a long story. You can
Call
do
it
it.
anything. Yes, female dummy.
Female dummy. Okay.
Okay.
Female dummy. Yes. So you change it. No, just leave it. Leave label. Go to change.
Change now. Yes.
Change. Then
okay. Add old and new
come to
value.
old and new variable. Yes.
Okay.
Then you now swap it.
Oh yeah, swap it. You can do it, but it's a long journey.
Yeah, it's actually long journey. I agree now. It's long journey. So 1 becomes 0. You understand?
Okay. 1. New value will be 0.
It will be 0.
Yes.
Then add. Then 2 will become 1. It's a long journey, naturally. I agree with Dr. Dolapo.
So you see how to that one also, you now go and label it. So is even when
yes. It's a long journey.
So now, Dr. Ikobo, do you have a data? Dr. Balogun, still stay. Just leave your data there. Just wait. Dr. Ikobo, do you have your data set you can share? Because some of these things, if you don't participate, you think you know it, you will not get it. is handsome. Okay, this one that Dr. Balogun is because he tried to do it. That's why now, as he has tried now, in the process of trying to do it and mess it up, you will get to know the right thing. But if you don't try it with your hand, okay, now, Dr. Balogun.
Yes.
You have something like blood sugar inside this data?
No.
So you have, I can see BMI. You have BMI?
No.
You don't have any quantitative variable there? You don't have PCV, hemoglobin concentration?
No. I don't have those ones.
Okay.
I want to check whether I can bring.
Okay.
Yeah.
And share your own.
All these variables, Dr. Balogun, all these variables are categorical variables.
And most of them are yes.
Most of them are yes.
They are categorical.
You don't know that clinician like logistics. So most of the time, even if that personality was medical, when they are collecting it, they have already dichotomized it themselves.
That maximum size on CT, how is it coded? It's not a numeric.
It's a numeric variable, yeah.
Okay, yeah, that would be numeric.
Maximum size,
yes, on CT.
It's not complete. The data is not complete. Let me see. Let's go to data view.
Check the data view.
Data view, yes.
It's still this on missing data. You can see there's some missing data there.
Okay.
Some people didn't do CT, some did.
Okay, let somebody bring the data value that have Dr. Ekobo, have you seen the data? All you need to do is just open your SPSS and share with us. That's all.
Look at age. This age is complete. Dr. Balogun, this age is complete. Age is complete.
Okay,
and it's a continuous variable.
What are you going to do now? Let's say you want to talk about age greater than a particular value. Let's choose a value now. I want to say age greater than a particular value. You want to
54.
Yes.
54.
What do you say?
Let's say 54. Age greater than 54.
Okay, age greater than 54. So
greater than 54.
Go to that select. Go to data. Go to data, not transform. If you want to range the age into more than 2 categories, you go to that transform. You use that method. But if it is only 2, you don't need to waste time. Just go to. No, you don't need to come here. Just go to data. Click on data. Then go to select cases. Move first of all, if condition. You know, all cases are selected. Then click on if.
If condition.
And click on if. Okay. You now move age in.
Okay, he has done that.
Greater than. Is here now? That's it in front of 7. 54.
Greater than on the yes.
Yeah, 54 is great.
Yes.
Continue. That's great.
Correct.
So go to the data editor window.
Go
to the variable view. Go to variable view now.
Sorry, I'm sharing something else.
No,
we can see now. Go to variable view.
Just go to variable view.
We can see it.
You can see it. Okay.
Yeah, okay. Yes. Variable view.
Now scroll down to the last. Scroll down to the last. You go to see your filter.
You see filter. You see filter.
Go to the last. Scroll to the last.
View. You see filter.
Down.
Okay. Variable view. Filter.
Yes. Scroll down. So you see that filter now.
So now that filter, change it to age more than 54. That's all. Just type age greater than 54. No spacing. Age greater than. Type it as word. It will it will not take that thing from you. It will not take it.
It will not accept this.
It will not accept it. It will not accept that greater than because
it will not accept greater than. It will not.
Let me try it now.
Yes.
Than 54. No, you can type 54 as figure there. Doesn't matter. It is sign that you will not take. You can type 54 greater than 54. Yeah, that's great. So you can remove this one. You can remove that one. Delete it. Delete that one.
Which one?
That one in the middle, yes. Age greater than this sign under label. Click on it and press on delete in your laptop. You remove it.
Okay.
Press on delete on your laptop. So now you can click on the value so that you rename it. Though it doesn't change anything, but so that it won't be saying selected, not selected. You click on selected and change it. Click on selected, change it to yes. Change it to yes there. Type yes. Change. Click on the other one and change it to no. Great. Okay. So go to your data back. If you don't go to your data, it has only selected before. Now go to your data, go to data, not say data view, go to data. That icon up. So that I help you remove those cancel. Then go to select cases. Click on all cases.
Okay.
It's not that one, just click on all cases. All cases. The first option. That's
Yes.
it. Okay.
Yes, I'm on it.
They say okay. Okay.
Yeah.
So if you look at it, you have created a variable now. There's a variable, if you look at it, if you go to your data view, you can see, go to your data view, you go to see it. No, you've already, go to your data view. You scroll to the last, you go to see as the last one. That's a data, yes or no. So can you see now? That's the way, Dr. Ikobo, that's the way you do. If it is diabetes now, you want to treat diabetes, not diabetes. When you click on the blood sugar, you say greater than or equal to 126. You go and say, that's all. You go and relabel it. Just say diabetic. You relabel it as diabetic. And go and change the selected as yes, not selected as no. That's all. You have created a new variable, diabetic, yes or no. Does it make sense? And that yes is 1, no is 0. So you can use it even directly as a regression. Imagine if maybe the attribute you are looking for, the people that are diabetic, they don't have the attribute. The people that are not diabetic, they have the attribute more. If you want to code the people that are not diabetic as 0 and diabetes as 1, you can go and create another one and say select diabetic. When you select that, you now say is equal to 0. You know, you already created diabetes as yes, no diabetes no. You now say select diabetes is equal to 0. In that case, it will select those who and code them as 1. So you now go and label this as a non-diabetic. Can you see? That one is a dummy for non-diabetic. So those are the things. So once you lay your hand on the data, you know you must understand the science, then the practical. So your science, to me, the knowledge is more important than the practical, because the knowledge first, then you now look for way to practicalize it. If you just want to practicalize, you don't have the knowledge. That is crookedness. Many people that they are analyzing data for people, destroying people's data, that's the type of thing. You know, if some of those people, if you give them SPSS to help you enter data, you now discover that, look, this is analyzed. So you know, say, the next time they just put their phone number, say, if you want to analyze your data, just call this number. Because they have already said, after you enter the data, this is analyzed now. That's all. To them, that is all. But that is not all. You must understand what you are doing. Then you now have the machine to do what you want him to do for you. I don't know if there's any further question there. So that we just wrap up today. You can stop sharing. Stop sharing. Yeah, this is 8:30 something. So we stop now, but let's quickly look at the last part of, so that we just finish the correlation. So what I was discussing the other time, the strength of correlation, the direction. So instead of people using instead of you using the p-value to judge correlation. So look at some people come, though they come with different things. They look at, I just look for one that is simple to understand. Look at this. Negligible, less than 0.2. 0.2 to 0.4. Low relationship, that is low correlation. Then 4 to, some people call it, well, low correlation, yes. Then 4 to 7, moderate correlation. 0.4 to 0.0 rather. 0.7 to 0.9 high. And 0. They say greater than very high. But 1 is perfect. 1 perfect. Look at another person, something down here. Perfect 1, yes. And it can be positive or negative. 0.75 to 1, that is strong. Moderate 0.5 to 0.85. To me, I prefer this one because it has this word perfect. And because some people, I know that many people say 0.5 to 0.8 is moderate. So 0.75 and 0.8 mean they say moderate. 0.25 to 0.5 weak, yes. Then less than 0.25 can say is negligible. So it can be on positive or negative side. That's how to interpret. We don't interpret it with p-value. Make no sense. So now, lastly, let's look at, if you remember when we were trying to run the correlation, you see, it give you you say bivariate. You see partial there. Bivariate just means the correlation between two variables, or you call it zero order. That's what we usually do. That is between these two variables. That's all. But if you want to do correlation, look at this first diagram. The correlation between A and Y, and you see it can go on both sides. That's why the arrow, we are not saying A lead to Y or Y lead to A. It's on both sides. But there is another variable B, which is somewhere, but you didn't make mention of it. That is what partial bivariate does. But if you look at partial, this last one, you want to look at correlation between A and Y, but you also control for the effect of B on A and effect of B on Y. So in that case, that is partial correlation. So you are looking at correlation between two variables, but you know that there's another variable that may affect both of them. You try to remove the effect of that variable on both of them. That is partial correlation. But if you try to remove the effect of the other variable on only one of them, not both of them, like in this case now, semi-partial, you are trying to correlate A and Y, but you are removing the effect of B from A. That is semi-partial. So when you are doing this, just some complex for you to understand it, some complex mathematical, in fact, you have to draw some Venn diagram. But the purpose is, nobody actually do that because the purpose is actually taken care of when you are doing regression. Because what they are trying to do is that they are trying to talk about dependent and independent. They are removing confounder. The essence of doing partial correlation, semi-partial, to remove confounder. The correlation, as you see, even if you do that, does not even solve the effect of confounder, because it's difficult for you to say, okay, this is independent and dependent. And this issue of independent and dependent, the regression has taken care of it. Removing confounder, the regression has taken care of it. So that is why you see the issue of semi-partial, partial is not so popular. And after all, when you are even doing that, when you are doing regression, sometimes you have to load in a lot of variables, controlling for a lot of effect of other variables, many variables, which to do that with partial and semi-partial correlation is going to be cumbersome. And that is just for you to understand the concept of that, because Professor Wakwe was raising a question that when they start talking about partial, semi-partial, you hear of DV, dependent variable, IV, independent variable, even in correlation, when they start talking about that. Their headache is taken care of by education. I think we'll stop here for today. I don't know if there's any question. So we are trying to trash out correlation. And tomorrow we go to regression. Yes?
Thank you very much. Well done.
Okay,
Sorry,
thank you.
if we go to our SPSS,
Okay.
under that correlates,
You see distance.
the distances and canonical correlation, are they relevant to us?
Yes, the canonical correlation, that one is, the canonical analysis is part of what we call multivariate analysis. So that one is even beyond what we are doing here. But the distance, to be sincere, I've been trying to find out what that distance means. I don't know. I'm trying to find out what that distance means. Does it mean partial? But if you look at, there's no partial there. There's no semi-partial option there. And also, some of these software also, all of them have their, the strength and weaknesses. Sometimes people rate SPSS, Starter, SAS, different thing, and talk about what this one can do better, where this one is good, where this one is not so good. So they have their strength and weaknesses. I'm trying to look for the semi-partial and partial there. I didn't say I saw distant and canonical. But I understand what the canonical mean, but I don't know what
that has partial.
Okay, it has partial, yes, but it also has distance. And yes, sorry, it has partial because I even run the partial. It's true. I even run the partial. But the distance, I don't actually know. I would just check. I don't know what it means. But the canonical correlation is beyond what they are doing, because what it does is to look at how many variables, how many variables affect Y and X, and how those different variables affect their correlation. Can you see now? So in that case, it fits into the area of statistical multivariate analysis, where we have more than one outcome at the same time and more than one exposure at the same time. So it is only time permit that we delve into that, because if few people look at the correlation, people want to listen to correlation. How many do you want to do to have the training on multivariate analysis of variance, factor analysis, all those stuff, which fall into that category of statistics? But even survival analysis, I have training on there and run it. But how many people want to learn it? Not talk about canonical correlation, analysis. So we just leave that one. So common thing occur commonly. That's the principle we are following in Nigeria. Common thing. Though, to be sincere with you, also most of the problem also are solved with some. It's only in extreme cases. In some extreme cases that you actually need some of them. To be sincere with you. So it's not something that somebody have to say, I have to be learning. To be sincere with you. So the most important thing first. That's just it. So any other one?
Exactly.